Okay, this is video 3 for the electrostatics unit notes. This one we're going to start with something of a conceptual thing. We're going to talk about electric potential. And really what this is the electric potential energy per unit charge. You may know this more informally as voltage. We're going to work with circuits later on, and voltage will become very important. For the time being, we'll just refer to it as either electric potential or potential. Now, I do have a warning here. Electric potential energy and electric potential are different things. They each have their own units. Electric potential energy was measured with a joule. Electric potential is measured with the volt. So what an electric potential is then, or what a volt would be then, would be a joule per coulomb. And this was named after an Italian scientist, Alessandro Volta. Now, for potential, the way we calculate it, for electric potential, it's the change in electric potential energy in a circuit is the change in potential energy per unit charge. So the potential, which I use this V right here, equals the electric potential energy per charge. So remember, we use a U for potential energy and a Q for charge. So from the previous video, what we learned was the electric potential energy was K QQ over R. I'm going to use a lowercase q for a test charge and a capital Q for a thing being tested. And then what I'm going to divide this by is a test charge. And hopefully what you can see then is that the two Q's will cancel out, and I'm left with KQ over R. Now we also have something called the principle of superposition. And basically what we can do is we can take all of the different potentials and simply add them up. So, we have this is actually the reason why if you take multiple batteries and put them in series, put them one after another, their voltages add together. So if you open up the back of a TV remote, you'll see two AAA batteries. A AAA battery has a voltage of 1.5 volts. So together, those two batteries gives you 3 volts. And what's really nice about this is that there's no vectors. Since it's based off of energy, there's no vectors. So this is a scalar addition. It is possible for the electric potential to be negative. And that's something we'll take a look at later on. All right, now when a point charge moves from one point to another point within an electric field, and electric field is something we'll talk about later in this video, it will have a different potential at the first point than it does at the second. Then by subtracting those two potentials, we get something called the potential difference. And this gives us an electric force acting on a charged particle. And with the electric force, it's always directed towards lower electric potential energy, or lower electric potential, because the higher the electric potential energy, the higher the electric potential, and the lower the energy, the lower the potential. So electric forces acting on a charged particle will always be directed towards the lower electric potential. Something else, electric fields, again we'll talk about this later in this video, they always point in the direction of decreasing electric potential. So here's something that we have here. We have two plates, and let's say the top plate has a positive charge placed on it, and the bottom plate has a negative charge, or we can just separate them, 12 volts to 0 volts. Now we'll learn to call this a uniform electric field later, but the red lines here represent something. They represent electric potential. And notice how the first line is at 2 volts, 4, 6, 8, 10, and then all the way up to 12 volts. Everything on this line, every charge on this line will have the same electric potential. So if I take a look at this line right here, every charge will be at an electric potential of 8 volts. Now, since the voltage is the same no matter where you are, on this line, since that voltage will be the same, this has a special name. It's called an equipotential line. And that's because everything, or every charge on that line, has an equal potential. It's all at 8 volts. If a charge were to move from, let's say, this line right here to this line right here, it would have a potential difference of 6 minus 2, or 4 volts. All right. Now, so far we've seen, this example I just shown you was where the electric field is uniform and all the lines are uniform. And that's, 2 parallel plates. But let's say we have a point charge, something where an electric field might look different. Again, I would have equal potential lines, except now they would be circular. So this one out here might be at 2 volts, 4 volts, 6 volts. And notice how the potential becomes greater as you get closer to the charge. And again, everything on this line, this is an equal potential line, everything on this line would have the same potential. Now let's say we have something really strange. Let's say we have a water molecule. Now, in a water molecule, half of it's positive, half of it's negative. The equal potential lines are going to look different. We'd have some for the positive and we'd have some for the negative. So some of these equal potential lines can look a little different depending upon the charge configuration and everything else. Okay, I've mentioned electric fields a little bit, so now let's really start talking about what they are. Electric fields and electric field lines are vectors, and they point in the direction of least electric potential, and they represent the path that a positive charge would take. So for instance, if I take a look at this positive charge here, if I were to draw the equal potential lines, I would have a really high potential, so let's say 20 volts. And then as I get farther away, the potential decreases. And since this relationship here, potential, which was KQ over R, the potential is proportional to 1 over R. So these lines, as they get farther away, should become farther spaced out, and they should be uniform. So looking at this then, the electric field lines should be pointing from larger potential to least potential. And also, these electric field lines must be perpendicular to the equal potential lines. They are always perpendicular. So the electric field for a positive charge would be something that's diverging away. All right, now let's take a look at a negative charge. Negative charges are a little different. Uh, take a look at our model for electric potential. If the charge is negative, the potential will be negative. The equal potential lines will look the same or similar, but I'd have, like, let's say -2, -8, -10. So notice that this time, to get a decreasing, pointing in, these electric field lines need to point in the direction of decreasing potential. This time, it's converging. It's towards. I got to make sure I draw these lines all perpendicular to my charge, or to my equal potential lines. So again, for a positive charge, the field is diverging. For a negative charge, the field is converging. And the field must be perpendicular to the equal potential lines. All right, let's take a look at a system where we have two charges. And I'm assuming that these charges are equal. Well, first off, if these charges are equal, I'm going to have a line down the center at 0 volts. Because remember the principle of superposition, delta, or not delta V, the potential equals the sum of all potentials. Well, in this case, I've got two potentials, and one of them is negative. And they all have the same value of Q and equal distance between. So, if you do the math in your head, you should see that at the point exactly in between these two, if I add together these two potentials, I would get 0 volts. The rest of the lines would look something like this. All right, now we just need to draw in our field lines. Well, something else to remember, for a positive charge, let's say that this is, 10 volts, 5 volts, 3 volts, 0 volts, and this would be like, -3, -5, -10. These field lines, which go from large to lower, that means that in the center, I would have a field line that would go this way. And we want to make sure we keep these electric field lines perpendicular to the equal potential lines. These field lines would go out to infinity, come back from infinity. And that would be the electric field between those two charges. Let's take a look at another example. This time the charges are not equal. So here I have a +2 charge and a -1 charge. And we can see how the equal potential lines kind of dominate over the lower charge. So if I were to draw the electric field here, and again I have to make sure that I keep these perpendicular. we see that the electric field is dominating, or the electric field of the larger charge is kind of dominating the electric field of the weaker charge. Also notice that I'm not crossing any of my field lines. All the field lines are distinct and they're different. Now, the vector field gives, as a function of position, the value of a physical quantity that's described by a vector. So vector fields, such as electric fields, are represented by field vectors. They indicate direction and magnitude, so they are vectors. When more than one source object with mass or charge is present, the field value can be determined by vector addition. So we can add vectors for electric fields. And then a known vector field can be used to make inferences about number, relative size, location, sources, and things like that. Now, the way we calculate electric fields, really any kind of field, what this will be, first off, we use a capital E for the symbol for electric field, and it's a vector. And that will equal the electric force acting on a charged particle divided by a test charge. So, remember that electric force is K Q1 Q2 over R squared in the R hat direction. So then the way I can write this is K test charge, charge of object being, the charge of an object being studied. So we see that the electric field is K Q over R squared, and it would be in some R direction. Now this is always true. This should work every single time. But we can look at an easier one if I have a uniform field. Now, there's basically two types of electric fields. We have our non-uniform field, and notice how the field lines are getting farther apart. They are getting weaker as the distance increases. It's just a non-uniform field. But we can also have a uniform. Let's say I take two parallel plates. Give a positive charge to the top plate, a negative charge to the bottom plate. Here I would have a nice uniform electric field. The field lines are evenly spaced, they're the same length. No matter where I look inside that region, the electric field would have the same value. Oh, and the units for electric field, if we look at force per coulomb, the Newton per coulomb, that's the unit. So no matter where I go in this field, it will always have the same unit of newtons per coulomb. For this case, the electric field can equal the change in electric potential over distance, where the distance will be somewhere in between those two plates. So this is a quick way of calculating electric fields, but it is not always true. It's only true for a uniform field. All right. This concludes the notes. We will do plenty of practice in class to help solidify some of these topics.